Okay, so here's what I'm going to do. I would like your feedback here. I'm going to show you something. This is a gas, and we have some gas particles moving. It is currently at 27 degrees Celsius. Okay. I want everybody to make a prediction in the chat. Tell me, if I were to heat this up to say 600 degrees Celsius, what will happen to all of those particles? What will change? Go ahead and type your answer in the chat for me, please. Something about those particles will change, yes. Okay, so I got quite a few responses here. I got they will move faster, they will get faster, they will speed up, they'll start moving faster, they'll be more active, lots of ways to put this. They will be moving extremely faster. They will expand. Okay, they will expand. Let's take a look here. I'm going to heat them up now. Are they moving faster? Yes, they are. So by adding more energy to them, what changes? Particles start to move quicker. So temperature is actually basically speed. It's like how fast these particles are moving. Okay. So that is what temperature is. It's just the motion of these particles, and temperature is an average. Now, if I look at it, not all of them are moving fast. Like here's one, oh, just got bumped. There's one that's moving slowly right there. This one's moving fast. They're all slightly different speeds, but the average speed of these, they're moving a lot faster than they were. Okay. Now, if I were to cool it back down, they slow way, way down. Okay. You get a lot slower. Right? So that's what temperature is. It's basically how fast they're moving here, moving around. All right. Questions on that? I had one or two of you guys who said that it will actually expand. As long as this is like a solid container here. If it was like a balloon, yes, it would. It would expand. But because it's not like a balloon, it's just like a solid container here that I have this in. It's just they just get faster. That's actually what temperature is. It's just speed. Okay. Now I had a few of you mention the pressure. Okay. Now as I heat it, I want you guys to pay attention to this pressure gauge. Currently, it's at like 6 or 7. So if I heat it up, they move faster and they move faster and they move faster. And what happens to the pressure? See how it's increasing? Why? Why is it when I heat them up and they move faster, why does the pressure increase? Why does the pressure increase when I increase the temperature and make them move faster? Okay. Got a couple of good answers here. I got Gay-Lussac's law. Temperature and pressure are directly related. Okay. Which is true. So Gay-Lussac's law, but what is like the explanation behind why the pressure increases. I got a couple people who are going that route. So here's one. Because they're moving faster, the particles are hitting the walls more often. Okay, which is true. If they're moving faster, they're going to hit the walls more often. Remember that pressure is particles running into and hitting the walls. Okay, so pressure is particles running into, hitting the walls. So if they're moving faster, they're going to hit the walls more often. They're also going to hit the walls with more force. Somebody else mentioned that as well. So they're going to hit harder if they're moving faster. So that is why the pressure increases, because pressure and temperature are directly related. And the reason why is because they're moving faster, they're going to hit more often, and they're going to hit harder, right? That's the relationship between pressure and temperature. Questions? So let's go ahead and write down something about this. Let's talk about what pressure actually is. Okay. So air pressure, pressure around us. Air pressure is the force that's exerted by a gas particle whenever it collides with a surface. So we have gas particles that are in the air, they're moving around, they're just going to bump into something. And when they do, they just bump into it and push on it a little because they collide with it. That's what air pressure is. Okay. And here's a pretty good picture of air pressure. Okay. So, and I would recommend drawing this picture in your notes. We've got little air particles moving around. You can see in this picture, we got a little motion here of them moving, and they're going to hit the wall, bounce off of it. And I love the little lines here that kind of show that it's pushing on it and giving a little force there against the wall. All right. That's what air pressure is. It's the force that's being exerted whenever they collide. They're hitting. That's it. That's what pressure is. Hitting. Okay. If you increase the temperature, they're going to hit more often. They're going to hit harder. So it's more pressure. And that's Gay-Lussac's law, why pressure and temperature are related. Now, today's lesson is all about the idea of pressure and kind of going over some of the intricacies of it. Okay. So I want to point something out about what we're talking about today. And this is very important. When I start talking about temperature and pressure, and people are like, hey, this is what he was explaining last week, I already know this. The thing is you don't. Okay, there's going to be some things here that I'm going to say that you do not know. In fact, they are completely the opposite of what you think. Right? If I were to ask some of the questions that I'm going to ask you today to basically all of Americans, 90% of Americans would probably get it wrong. So this is essentially me attempting to take something that is common sense but wrong and trying to make it like so you understand that it's wrong and here's what's actually like going on. Okay, because there is a few ideas about pressure out there that are like ingrained in people's brains. And today I am going to try and root those ideas out so you can actually understand what's going on. Okay, so when I'm talking here, I want to point out there will be points where you think I'm just kind of blabbering on. Please pay close attention. There are some things I'm going to say that are going to essentially like blow your mind. You'll be like, what? What did he just say? So first thing I want to kind of point out, there's air around you right now. There's air around you, all around you. And that air is running into you and it's colliding with you and it's pushing on you. Okay. It is constantly pushing on you, but you can't feel it. Why? It's because you're used to it. Okay. The air around you is constantly like running into you. You got air particles pushing on you, and it's just little itty bitty air particles that run into you and collide with you. And it gives a little bit of a push. All right. Now, there's a lot of air around you. The air around you is actually a significant force. It is extremely powerful. Okay. Now it surrounds you. It pushes on every part of your body. It pushes on your head down. It pushes sideways. It pushes up. Like I have air hitting my hand and pushing upward on me and colliding with it and causing pressure here. how hard does the air actually push? Well, you can't really feel this, but I want you guys to take a look at this bar here that I have. Okay, this bar weighs 14.7 pounds. All right, this is heavy. It's like the weight of a bowling ball. All right, now the air pushes 14.7 pounds on every square inch of your body, all over. So I'm going to take this and I'm going to actually raise it. And the base here is actually an inch by inch. So this is a square inch. So this is how much force is actually being pushed down on you or sideways on you on every square inch of your entire body. It is the weight of this bar directly onto a square inch of your body. It is a lot. The air around us is a significant force. It pushes very hard. Even though each individual molecule is not a lot of force, you have a lot of air around you right now. Whoa. It's okay. You have a lot of air around you right now, and it is pushing really hard on you just because there's so much air molecules actually hitting you. And it all adds up. It just keeps adding up. Okay. Now, we are, in fact, used to it. In fact, if we don't have that pressure on us, we would die. So we need the air pressure because we evolved in pressure. And so us as a species, in fact, all species basically that live in the atmosphere need that air around them to push on them. There are a few species that don't live in the air like they live in the ocean. They require different amounts of pressure. For example, the water pressure at the bottom of the oceans is extremely high. And so the fish and other organisms that live way down there, they're used to a much higher pressure pushing on them. And when you actually bring them up to the surface, it kills them. And it actually, like, they will expand. How many of you guys have ever heard of a blobfish before? Ever seen pictures of it? They're really weird. They look blobby. Those actually look like regular fish when they're at the bottom of the ocean. They look like regular old fish. But when they bring them up, because they're used to the pressure down there, what happens is they're actually having to push back on the pressure. And so when they get up here, their bodies don't have that pressure pushing on them. So when they're pushing back, they just expand and they get all blobby and it distorts them and then they're dead. This is actually what would happen to us if we were to not have the air around us. So because the air is pushing on you, your skin is actually pushing back on the air at all times. And if you were to ever remove the air from around your body, it would still push, but there'd be nothing pushing it back. And so you would actually expand and kind of, not too much, but you kind of blow up a little and get all bloated. And there are some kind of disturbing videos out there of people like putting their hands in a vacuum and then removing the air, and their hand just kind of like expands and gets all bloaty and swollen. If you've ever taken a vacuum cleaner and like put it on your arm or something, like playing around with it, you felt that experience. Basically, you may think it's like sucking up your skin, but it's not. It's just removing the air above your skin. And then when you remove that air, your skin will actually expand into the vacuum. And so you are feeling that swelling of no air around it. You're constantly like pushing outward, but the air kind of pushes back. And that's what's normal for us. So you actually really want that air pushing on you. If you were to be exposed to the vacuum of space, you're going to expand. It's going to kill you. So, does anyone have any questions over this? All right, I'm going to ask you guys a few more questions about this little diagram here. So, is it really possible for us to go to Mars? Does it have the same pressure? Good question. It does not have the same pressure. It is actually about 1% of the air there. You would not actually be able to exist on the surface of Mars without a pressure suit. It's not exactly the full vacuum but it's like 99% less. So, yeah, if we actually go to Mars, we would have to wear suits the entire time we were outside. There's a little bit of pressure there. I'm going to reset this here. Okay. So I have a question for you. If I were to heat it, the pressure would go up. Can anyone name another way that I can increase the pressure in here besides heating it? I want to increase the pressure. Okay, so I've got make the space smaller, compress it. Okay, so I'm going to do that. Right now the pressure is about 6. So I'm going to make it smaller. And you guys are right. If I compress it, it makes the pressure go up. Why? Why does compressing it and making it smaller like that make the pressure go up? Think about what pressure is. It's particles colliding it. There's less space to move around, but why would that increase the pressure? There we go. So less room means that they're going to actually hit the walls more. Like if you make them closer, then they're going to run into the walls more often, more pressure. They're going to push on it hard. Okay, just because they're running into it more because there's less room to move around. If I were to do the opposite and expand it, now they're all spread out. And so the pressure drops. We're down to like 4 atmospheres. Okay, because they're just not hitting the walls nearly as often because there's more walls to hit. It's all spread out. Okay, so we kind of go back to somewhat normal here. So that's one way that I can change the pressure is I can change the size, compress it or contract it. All right, then they're going to hit the walls either more or less depending on the size of the container. Another way, let me go back up here. I got a couple people who had a few more ideas. Another way I could actually change it, add more particles. So if I were to actually add more to it, now there's more air in there, and so there's going to be more particles hitting the walls. So yeah, there's basically 3 ways to change a pressure. You can either change its temperature, you can change the space that it's in, changing how many times it runs into the walls, or you can add more air, take air away, and that will actually change like how much air is hitting the sides. So 3 ways to actually adjust the pressure here. All right. Now, remember how I mentioned, I'm gonna come back to that. I got a slide for this. So go ahead and write this down. So air pressure is dependent on the temperature, how fast they're moving. It also depends on the density. I'm gonna combine the idea of how much I have and how much space it's spread out over into one idea. It's density, like how many air particles actually around you. If you give it more room, they spread out, so there's less around you. Less air to collide into you. So it's how much air you have, how much space it takes up, that's density. And then you have temperature, how fast are they moving? If they're moving faster, they're going to hit more often and with a greater force. Okay. Now I got a little demo that I want to show you guys. Camera ready here. Now you can't see this yet, but I'm going to pull it up here in just a minute. Okay, so I'm going to pull up this camera. Make sure I can actually see. Got to tilt it down. Okay, so what I have here, guys, is I have a can and I've got it on a heater. It's like heating up here, so I'm making it hot. I got this nice and high. I'm waiting for it to heat up. That's why I was like, hey, I paused for a second. It's not quite hot enough. It's getting there. I can almost see some of the steam coming off of it. But what's happening here is as I heat up the air inside the can, the air is moving faster, okay? And it's going to push on the sides of the can inside the can more. However, it is open, okay? So it's open to the atmosphere right here. So even though it's pushing, it does have a place for that extra air pressure to escape. Like there are particles coming out of this. My hand, there's like a nice breeze coming out. As that pressure increases, they're basically expanding and coming outward, okay? Now there is air around the can as well that's pushing inward on the can. Now with a normal can, The air in the can and the air outside the can is the same. So it pushes on the can just as much as it pushes in the can. So they're equal forces. Now, it's still equal forces here, but I am increasing the pressure inside this can right now. Okay, and it's just able to escape there. Now, what I'm going to do is I'm going to take this can, and I have here a bucket of ice water. So it's really cold water here. And as soon as I get it hot enough, and I know that I have a high pressure here inside this can, I'm going to dunk it in the ice water. Now, that's going to slow the particles way down. So these particles are going to slow way down inside, right? And that means that the pressure inside the can is going to go way down. So we're going to have very little pressure inside this can. But the outside, the air outside it is not going to change. Okay, so I think it's hot enough here. You can see if I see a little steam coming out. Not quite hot enough. Give it a second here. Come on. All right, I think it's hot enough now. I can hear it bubbling. I put just like a tiny bit of water in there just to make sure I knew it was hot. All right, so I'm going to take it and I'm going to basically flip it over so I can actually seal it off and then dunk it in the cold. Ready? 3, 2, 1. Ah, it didn't work. It's not got it hot enough. We're going to try it again. I'll come back to this in a minute. Okay. I'm going to go to the next slide while we wait for that to warm up. I'll come back, I promise. All right, so as you change your elevation, you also change your pressure, okay? So where we have the least amount of pressure is actually the highest elevation. So if you go up to a mountaintop, there's not going to be as much air up there, okay? And because there's not as much air, it's not going to have as much pressure. The pressure is going to decrease the higher you get in elevation. Now, if you go lower, if you like go down a mountain or down into a valley, then the amount of air is actually going to increase. So you will have an increase in pressure. The places with the highest pressure on the planet are going to be in the lowest areas. And this is all due to gravity. I just had somebody yell, gravity. It's all due to gravity. If you think about it, like water flows downhill. Well, so does air. If you put air on something, it will flow downhill. So it will kind of flow downward and then pool in the low areas on the earth, which happen to be where the water pools as well. So over by the seas, by the oceans, is where you're going to have the lowest elevations. And so that's where the air is going to pool. And so by the ocean is where you have the most air. And so it's going to be the highest pressure over by the ocean. Okay, when you go up on a mountain, you get less air because it keeps flowing down the mountain. Even if it comes back up there, it flows right on down. So there's less pressure up there. And the higher you go, the less pressure you're going to have. So as you go up into the atmosphere, even higher than a mountain, you're going to get even less air. And so the pressure goes down. So an airplane has very little air around the plane. It does have some because it's essentially what's holding it up, but it needs to actually have that plane pressurized. If it doesn't, that could be bad. Okay. If you've ever seen a movie where like they like blow out a door or window or something, then like all of the stuff kind of rushes out. That's an exaggeration, but it's not exactly wrong. Okay. When you actually like blow a window out of an airplane, because there's a high pressure in the airplane, all of that air is going to rush right out that hole. It only lasts for a few seconds and it's usually not as dramatic as Hollywood makes it, but it does actually happen. Stuff will just kind of like be blown out there. Now, commercial airplanes do not fly high enough where if that actually happened, people would immediately like start to swell and burst and die from the lack of air around them. They don't fly that high. Only military planes are going to fly that high, which is why when you're in the military and you fly one of those jets at the high levels, they're going to make you wear a flight suit, which actually protects you from some of that. All right, so this is actually hot enough now. I think it's hot enough. Let's try this again. So hot air, cooled down. There we go. So as soon as it cools, this off. As soon as it cools, there's less pressure inside the can. And because there's less pressure inside the can, the outside air around it, which it was basically equal to it when it was getting warm up. So we had pressure in and out. As soon as the pressure inside went down, suddenly the outside air was actually able to crush it. And it's pretty powerful. I mean, look how small it actually was able to make it there. I mean, if I took a regular can, it's basically the air pushing on it and crushing it. And even I can't really get it that small without working in it for a minute. This was instantaneous. It was just like, and then it was done. Okay, so that's all the outside air pushing on it. It's a pretty powerful force. So questions on that? Okay, I'm going to show you guys a little video, and I'm going to pause this video occasionally to try to explain a few things as we watch it, okay? So let me kind of pull it up here. Are you guys getting the sound? Can you guys hear it? Just want to make sure. Okay, I want to make sure I had the settings right.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high.
I'm going to pause. I'm going to pause a few times and kind of ask you guys some questions here. So first question here, this is a pump. All right, if you've ever seen one of these pumps, it's essentially like it's a pipe that goes down into the ground where the water is, and then you use the pump, and then the water comes up the pipe so you can actually get it. It's essentially like a really tall straw. Now, it says it can only go up 10.3 meters. That's meters. A meter is about 3 feet. So we're talking about 35 feet-ish. Okay. So imagine you had a pipe that is 35 feet tall, and water goes up it. Okay. When you have a pump up the top. Can anyone explain to me how a pump works? Like, how does the water go up when you actually pump it? Why does the water go up? I got a couple of you guys are like, oh, I don't know. Or I've wondered that before. A couple of you guys are using the word pressure, but you're not quite getting the right thing. But so I think you guys understand this has something to do with pressure, since that's what we're talking about today. It does have something to do with pressure. I've had pressure brings it up, and pressure is being released, making the water shoot up. A couple people mentioned how it's sucking it up, or suction. Okay, let's see what they had to say.
Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water.
Sound good? So if you suck the air out, then that vacuum that's created will actually pull the liquid up, okay, and pull the liquid up, but it's only so powerful, it can only pull it up 10.3 meters, okay? That is wrong. Everything that I just said is wrong, okay? I want to make that absolutely clear. This is not sucking the water up. Okay. It is not creating a vacuum that pulls the water up. Right? I'm going to explain what it is doing, but I want to point out that this is usually how people explain this to me. And I would say 90% of Americans would explain this to me this way. You have a vacuum, you're removing the air, and it's basically sucking up that water. All right. That is not correct. I want to make that absolutely clear that that is not what's happening. Okay. Even though that's usually what common sense would say is happening. So what is happening?
However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further.
Okay, so I'm going to pause it here. Go back just a moment. I want you guys in your notes to draw that. Okay, so I'm going to kind of explain it here, but I want you to draw this diagram. So we have a container with some water in it, and then there's a tube. And what they did is they took the tube, they filled it full of water, and then they sealed it. They put a seal on it. Then they flipped the tube upside down and put it in the water. And then once they put it in the water, they removed the opening here. And they did it in such a way that air cannot get into the tube. Okay. So there's no way for the air to go into the tube once they open this. And water came out. All right. The water didn't just stay in the tube. Some of the water actually came out of the tube, which means that this little space up here is completely empty. There's nothing there. There's no air. There's nothing. There's absolutely nothing in this upper space right here. That is a vacuum. And this is the first time we were able to create a vacuum, all right, and know that it was a vacuum. So we've got air on the outside, just can't get its way in there. And so some of the water came out, nothing went in. That right there is a vacuum. But not all the water came out. Not all the water comes out. So what is going on here? Remember that air collides with stuff. So this air on the outside is actually colliding with the water. Okay, so it's pushing on the water. Try to use my mouth here to demonstrate it. We've got this air that's pushing on the water. It's colliding with it. Because it's pushing on the water, it actually pushes the water up the tube. Right? It pushes this water up the tube. And it can hold so much water up there. It can actually hold 14.7 pounds of water up the tube. And that's it. I just mentioned that that's how much the air pushes, 14.7 pounds. Well, it can actually hold 14.7 pounds of water up a tube higher than the surrounding water. Like you can push it up and hold that much water up there. That's all it can hold though. So anything greater than 14.7 and it can't push it any higher. So you're not going to get the water any higher. Because this is higher than that, like to fill the tube would weigh more than 14.7, some of that water did come out once they opened the bottom, creating this vacuum. But it can hold the rest. It can hold exactly 14.7 pounds of the water in the tube. Okay? And that is what is actually happening with a pump. When you actually remove the air above the water in the pipe, surrounding air will push it up the tube. Okay, but it has to have this vacuum. As soon as I were to say, take a hammer and break the top here and let some air in, now the air would be pushing down inside the tube and it would push all this water back out of the tube. until the two levels were even. Okay, but as long as there is no air in the tube pushing it down, the outside air can push it up. And this is the way one of those pumps work. You remove the air above it, and it's not pulling the water up. The outside air is pushing the water up. This is also how a straw works. If I were to take a straw and put in some water, what I do with my mouth is I remove the air in my mouth, and then there's like a vacuum above the water in the straw, and then the outside air actually pushes that water up. If you didn't have air around your liquid, then it won't go up. If you've ever had a straw where it like somehow got like sealed around there, and then it like didn't work, you're like, can't make it go up, and the straw just kind of collapses. That's because it's the outside air actually pushing the liquid up. And so if somehow that didn't have access to the air or didn't have air around it, it would not be able to push it up the straw, and so the straw doesn't work. Okay, the only thing you're doing is removing the air, but really what's happening is the air pushes liquid up the straw. And this is kind of like hard to wrap your head around. It's not sucking it up. The outside air pushes it up. Okay, questions on this? I'm gonna hit play again.
Level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall.
Okay, so most people are not very familiar, but if you're familiar with like what mercury is, it's a metal that is a liquid. It's the only metal that is a liquid, and it's, if you've ever had the chance to like see it or hold it in like a container, it's really cool. But it's extremely heavy, like extremely heavy. So I once had a jar of mercury. Like I was actually able to pick up a whole jar of mercury before. It's this really heavy metal. And it was about the size of this mug. Okay. Now, if I filled this mug with water, it would probably weigh about, a pound or so, something like that. But yeah, I mean, it'd be about a pound. If I were to fill this thing with mercury, though, like that whole jar, it is ridiculously heavy. This much mercury would weigh like 14 or 15 pounds, like ridiculously heavy. This is like the weight of a bowling ball condensed into just this little cup here. So if you ever have a chance to like hold mercury and like pick it up, it is surprisingly heavy. It is extremely dense. And it's just like, oh my gosh, I cannot believe how heavy this thing is. Like, it is hefty. So what he did is he took this other liquid that's heavier, and he did the same experiment. He just used the different liquid, used mercury, but because it's heavier, it was still pushing up 14.7 pounds of the mercury, but the tube didn't need to be as tall. So instead of 35 feet tall, it was only 76 centimeters, which is about 2.5 feet. Okay, so 2.5 feet tall, which is a little more reasonable in terms of height. So it's the same amount of weight in the tube. It's just less of it because it's so much heavier.
Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same.
Okay, so they jumped through this in like 10 seconds. This experiment here Pretty simple. You get two tubes. One, though, has like a big bulb at the top, so it's got more space up here. They filled them full of mercury. They flipped them upside down. They let the mercury come out, and it was still the same height for both of them. However, this one over here on the right, that one has a larger vacuum. That is a larger vacuum that is created here than what we have over here. Because this is a larger vacuum, if vacuums actually sucked the liquid up and pulled the liquid up, it should have pulled it higher. It didn't. Okay? This experiment proves something that is really hard to like just get your head around. And that is that there is no such thing as the entire concept of suck. That concept of I take a straw and I suck up the liquid, that whole thing is wrong. There's no such thing as sucking it up, because right here, if there was such a thing, this bigger vacuum would suck up the liquid higher, but it doesn't. Okay. And so it's not sucking it up. What's happening is the outside air is actually pushing it up. And there's just happens to be nothing in there. Okay. But there's no such thing as sucking. Suction, not real. It's fake. It doesn't exist.
The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Okay, so this right here, tried to stop it so the image was on there. This right here, this device that basically I had you guys draw and tried to explain how to use, that's something called a barometer. You can use a barometer to measure the air pressure because it's basically how high up that tube it is able to actually push the liquid. So we can either measure it by the weight of the liquid in there, or we can actually measure it by how high up it is. So we can measure it like in millimeters or inches, like the height of it, or we could just measure how much that liquid weighs. For example, 14.7 pounds, right? So there's multiple ways to measure pressure here using this device. Now, one thing I do want you to write down, and I want you to name it, this is called a barometer, by the way. But this idea here that I kind of went over, there is no such thing as suction. The entire concept of suction doesn't exist. Okay, they're like suck is not a thing. It doesn't actually happen. A vacuum, which is nothing, cannot do anything. It cannot pull anything up. Okay, what's actually going on is the air around it pushes things up, and without that air around it, it would not go up the tube or the straw. Okay, there's no such thing as suck. There's no such thing as suction. That whole concept doesn't actually exist. It's something we made up that doesn't actually exist. Doesn't even have any basis in reality, really. Whew. All right, so measuring pressure. Yeah, that's funny. I wonder if whoever discovered suction found this out and went, well, that sucks. That's good. So measuring pressure. First off, there's a couple of units that we use to measure pressure using this barometer. Okay, so here are the units that we typically use. Because it's about the height above it, I'm going to highlight these ones here first. Millimeters of mercury, how many millimeters that can push mercury up a tube. Okay, can just how high. And we can also have the English version of it, the American version. Inches of mercury. Okay, so how many inches can it push it up the tube? All right, and it's just millimeters and then the symbol for mercury, and then inches and then the symbol for mercury. Okay, so those are just the height it pushes up the tube. That's one way we can measure pressure. The other way we can measure pressure is by like how much it weighs. Okay, how much liquid the liquid would weigh. So how many pounds it can push up the tube per square inch of the tube. Okay, so pounds per square inch is one you might be familiar with. The other one, the metric version of that, is the Pascal. So kilopascals, kilo meaning 1,000 of them. Pascal is a unit of force. It's a unit of push, just like weight is. Okay, so it's similar to what a pound would be, but it's metric. Okay, so kilopascal is the metric version of pounds per square inch, dealing with weight. Atmospheres, this one right here. I'm sorry, I'm kind of doing this out of order, but an atmosphere is just because sometimes it's very beneficial to like explain and compare it to a normal atmosphere. So 1 atmosphere of pressure would be just normal atmosphere pressure. 2 atmospheres of pressure would be like saying it's double the atmospheric pressure. So normal atmospheric pressure is 14.7 pounds. So double that would be 29.4 pounds. So that would be 2 atmospheres of pressure. It's double the normal atmospheric pressure. Okay, so atmospheres is another one, just comparing it to how much normal atmospheric pressure is. And the last one here is torr. Now, torr, side note here, stands for Torricelli, the guy with like the bouncing hair who invented the barometer in the little video we just watched. So Torricelli is the guy who invented the barometer, and he was measuring how high the mercury actually went up the tube. He was measuring them in millimeters, but he decided to give that idea a specific name, like that unit of how high up it went, a special name. So he named it after himself. So he called it torr for Torricelli. However, when people like later on were looking at this and they're going, but all we're measuring is how high up it went. That's millimeters. We're measuring how many millimeters up it goes, pushes up the tube. Why are we calling it a torr? Like he invented this unit, but it is the same thing as a millimeter. Like a torr is a millimeter of mercury being pushed up the tube. So a torr is the same thing as a millimeter of mercury. Those are identical. He just gave it a special name because he invented it and he was like, I'm just going to be awesome like that. And nowadays, nobody uses it. Nobody, like, we all call it millimeters of mercury because it makes more sense. It's a millimeter. That's what the unit is, right? How high up the tube does it go, right? So normal atmospheric pressure, standard normal atmospheric pressure in all of these different units are the following. And make sure you write these down. You're going to need these for the worksheet today. Okay, so 1 atmosphere of pressure, it's normal, just 1 atmosphere, would be 101.325 kilopascals, which would be 760 millimeters of mercury or 760 torr. Okay, those are the same thing, which is 30 inches of mercury. So remember that mercury is Hg, so inches of mercury is what that stands for, which is 14.7 psi, pounds per square inch. Okay, 14.7 psi pushed up. So go ahead and take a moment to write these down. Make sure you have them written down because you're going to need them. And I'm going to walk you through how to convert one to the other. Okay. Yes, this is one of the few things where it's like I am not going to like just like normally it's like we're going to stick with liters and milliliters and not use ounces and gallons and things like that. No, this is one and we're actually going to talk about the American and the metric and all the different like weight versus height. Like, yeah, because they all get used all over. And so it's like, it's just easier to mention them all and tell you how to convert from one to the other. So a whole bunch of different units here. So because this is normal atmospheric pressure, this is how they're all equal. Okay. So 30 inches would be 760 millimeters, right? 760 millimeters of mercury would weigh 14.7 pounds, right? 30 inches of mercury would weigh 14.7 pounds, and 14.7 pounds converted into the metric equivalent of weight would be 101.325 kilopascals of weight, and it's all a normal 1 atmospheric pressure, okay? So converting from one to the other. Today's weather states that the pressure is 29.4 29.75 inches of mercury. What is the pressure in atmospheres? 29.75 inches of mercury. What would the pressure be in atmospheres? Okay, so that's my problem. I'll pull up my camera here. We have 29.75 inches of mercury, and I want to know how many atmospheres it is. So I'm going to take the 29.75 inches of mercury, and I'm going to times it by a factor. Okay. Now, the unit I have is inches of mercury. So inches of mercury goes on the bottom. Okay. And the unit I want is atmospheres. So atmospheres goes on top. This is exactly what we've been doing. Now I'm going to go and take those numbers that I just showed you on that slide and connect the right number to the right unit. So it's 1 atmosphere and 30.0 inches of mercury. Okay, the 30 goes with the inches, the 1 goes with the atmosphere. Inches of mercury on the bottom, because that's what I have. Atmospheres on top, and that's the setup. So 29.75 inches of mercury times 1 over 30 is 0.9916666 repeating. Okay, 6666 repeating. So I'm going to round that answer for sig figs. This one's got 1, 2, 3, and 4, but this one's only got 3. So I'm going to round it to 3. 1, 2, and 3. The next one's a 6, so it rounds up. It's going to be 0.992 atmospheres. So 29.75 inches of mercury is 0.992 atmospheres. It's a little lower than normal. It's actually slightly lower than normal today. Okay, according to that problem. Questions on that? Okay, so second problem here. My tire pressure is 32 psi. What is the pressure of my tires then in kilopascals? Okay, so pressure is 32 psi. What is the pressure of it in kilopascals? The same thing. I've got 32 psi, and I want to know how many kilopascals that would be. So 32 psi times it by a factor. Okay, I'm going to let you guys do this one. All right, psi on bottom, kilopascals on top. Go ahead and tell me the answer in the chat, please. Okay, so it's psi, so we're going to put the 14, and then it's 101.25 kilopascals on top. So 32 times 101 divided by 14.7 equals 205.714.286. Now, sig figs. This one's got 2, this one's got 3. So 2 is my lowest. So 1 and 2 get to 220 kilopascals. Questions? So I'm going to come back. And right now I've got a blue gas in here. It's bouncing around. It is, let's change it to Celsius, 27 degrees. Currently, the pressure is about 11 or 12. Let's go with 11. Okay. Now, what I'm going to do next, add more gas into it. The pressure is going to increase because I'm adding more gas, but I'm not going to add the same gas. So I've got these blue ones here and little red ones. So I'm going to add some red ones here. Now it looks pretty busy in there, and you can see the pressure did go up. It was, and now it's about 29. Okay, so it was 11.29 because now there's more particles hitting the sides and colliding with them and pushing them. Okay, now you may notice that the red are moving faster. That is because they have the same temperature, the same amount of energy as the blue, but the red ones are smaller. Because they are smaller, the same amount of energy means they're going to move faster. Okay, so it is speed, but it's also like if it's a larger molecule, it's going to be more with the same amount of energy, so same temperature. Okay, so they're smaller, but they're bouncing around, and now we're up to 29 atmospheres. What do you guys think the pressure is going to be if I remove the blue ones? Okay, with just the blue, it was 11. With blue and the red, it's 29. So if I remove the blue ones, what do you think pressure is going to be with just the red ones there? A couple of you guys are saying 18. Okay, let's go ahead and see. I'm going to remove the blue. Now it's about 16. Interesting. I add the blue back in. That's weird. I'm not getting the same answer. It was 29. Now it's just 26. So I do this a little differently here. It's going to do 50 and 50. Maybe that extra stuff is kind of throwing it off. Okay, let me show you. Okay, so the blue is 6. And then if I add some red in, it's 18. So 6 for just blue, 18, maybe 17. 17. Yeah, 17 for the red. And if I remove the blue, it goes down to 11. So here's my point. The pressure that these gases are exerting, if I have two different types of gases inside a container, the pressure is them colliding with the walls, okay? And because they're not really like touching, I mean, they bump into each other occasionally, but they're not really like connected. The blue runs into the walls and the red runs into the walls, and they're kind of independent of each other. Like the blue runs into the walls and pushes 6, and then the red runs into the walls and pushes 11. And so the amount of push on the walls is both the blue and the red. 6 plus 11, 17. Okay, so they add up. So that first time you guys were actually correct. You can basically like just add 2 pressures here because they're kind of independent of each other, but they add together when they're both in there. This idea here is something called Dalton's law of partial pressures. So if I have a mixture of gases of like red, green, and purple, they get together, each color in this mixture is going to give its own push. And so if this was pushing, let's say 5, and this was pushing, let's say 5, and this was pushing 7, then they just all add together and it would be like 17. Okay. So Dalton's law of partial pressures. The total pressure of a mixture of gases is going to be equal to the pressures of each gas in the mixture added together, the sum. So again, if this pushes 5 and this pushes 5 and this pushes 6 or 7, they can add them up. And so when they're all together, they're pushing 5 plus 5 plus 7, 17. Okay. Questions on this? All right. Last slide. Come on. So let's say I have a mixture of gas. It's made out of hydrogen and oxygen. Okay. It consists of hydrogen gas. And when I first put the hydrogen in, it was 480 millimeters of mercury. And then I put the oxygen in, and the total pressure was then 754 millimeters of mercury. Okay. So just hydrogen was 480. Put the oxygen in, and now the total pressure is 754. So what is the pressure of just the oxygen gas? Go ahead and send me your answers in the chat. What will the pressure of just the oxygen gas be? So yeah, it's 480, and then I add the oxygen, and now it's 754. So the oxygen would be the difference between these two numbers, 754 minus 480. So that would be 274 millimeters of mercury. 274 would be the pressure of just the oxygen. Okay. And yeah, that's it. That is the idea of adding pressures based on several different types of gases. So make sure you have said something today so that I can count you guys here when I do attendance here in a few minutes. I'm going to post this online if you guys want to check it out later, or if you had a bad connection and you missed a part of it. But that is it for the notes today. I want you guys to do the worksheet, Kinetic Molecular Theory 2 next. All right, it is 274. All right, but that's basically like going over and practicing everything I just went over. Kinetic Molecular Theory Worksheet 2. Otherwise, I will see you guys tomorrow.